Hello and welcome back to Compiler Programming. In between the videos, I did a small cleanup and separated our spec file into multiple different files because it was growing a bit too long for my test. It was more than 1,000 lines, and this is usually where I stop and think like, all of this stuff has actually to be in one file, or can we separate it into multiple ones? So now we have an encoding file that for now is quite small and just has this enums that we use for our encoding stuff and the main encode procedure, which is still gonna grow quite a bit. So it's actually a good idea to separate it into a different file. All the value related stuff, whether it is the definitions or helper functions, is now in a value header file or value implementation file, so we know where to look for those as well. And these ones hopefully will not be changed too often, so it's a good thing to separate them out. Now, for today's video, I think it is time to start dealing with arithmetic operations a bit better. So as you can see, we here have a to-do to not make our add operation mutate one of the operands that is passed to it. This will require a bit of setup, but I think we can make it happen. So the first thing is, let's rename it from mutating plus to just add, or actually add is already exists, so let's keep it as plus. And instead of an operand, it should return as a value. And it also should accept two values instead of two operands. And this is where we also can start doing a bit of type checking. Or at least make a comment that this is where should it be. So do type check values. But for now, we'll just assume they are correct types, or they are the same type. I mean, for the CPU in the end, it doesn't really matter what the type is, but for our sanity, it probably makes sense to do some kind of type checking here. Okay. Now we need to create this temporary value that will be our result. And we have a few choices here. So if we want this function to be, we need to decide how generic we want this function to be. What do I mean? So the first thing is that value A and value B might be, for example, both memory addresses. In this case, there is simply no instruction that can deal with that, and that means we can't really make that addition. So what we can do instead is we can always make operations on arrayx register, which is one of the registers considered volatile. That means that if you call another function, that it can mess up with that register. In particular, the return values usually is done inside arrayx, but also inside of our function. Arrayx is a good temporary register for various reasons. One of them is that if we look at the encodings, a lot of the instructions will actually have a special form that addresses arrayx directly. So instead of using, let's say, this form of instruction where we have to specify which register we are using, we can use this form with arrayx directly, and it is a bit shorter, meaning it's a bit faster in the end because the processor has to decode less bytes, and the less bytes you have in your functions, the more of it fits into the processor cache, and typically that's better. Anyhow, so let's consider this. So we say that value A and value B should never be array X registers. So let's add this check, and we will call it void assert not a register. No, not AX, not register AX. And it will get a pointer to a value. Value star value. So first we will assert that it's not null. Then we assert that, or we say if value operand type is operand type register, we assert that value operand reg index, or we can say like this, is not equal. Actually, I think we can't compare this with it. So register index is not 0, or we can say array X reg index. Either of those will be fine. And we check for both of the values. And one of the ways that the value can end up being in X register is whenever we do our function call. So this is another place where we will need to make a change to, instead of just keeping it there, we will store it inside stack memory and then kind of use that as our return value. But for now, let's continue with this function. Okay, we check that none of them are AX register, and meaning that we can start using our AX register as a temporary one. So the first thing that we do is we need to move into array X, and here we will need to deal with size. So in reality, we should move into array X. Instead, we should move into whatever is the size of the other operand. But for now, we can probably get away with not doing that. Let's see. So a.operand. Now we have one of them in the right place, and we need to have another one in the we need to now add second one to array X, and this form is always safe to do, like at least in x86. If one of your if the first operand is a register, then if you look at the table here, no matter what is the other operand, so we have a register memory, we have register, we have immediate value, so no matter what it is, it should work, with an exception of 64-bit value. So we cannot really use 64-bit immediate for this addition. In most cases, though, this one will be perfectly fine as a substitute, but this is something we need to take into account. I'm not sure, I don't remember yet exactly where we use this plus, so depending on where we do, we will need to take some action. Maybe let's do something like deal with immediate 64. And the way we can deal with that is we can we can always take up, for example, this form, and make sure that if you have immediate 64, we will first put it in register or inside or somewhere on the stack, and then we will just read it from the stack. Okay. Let me think about this. So we moved the first argument into array X. Now we can do our addition, but instead of A and B, we say array X and B operand. So we are done with our addition, but we need to figure out what to return, and we need to return a new temporary value, and we need to make a choice of who is responsible for freeing array X. And I think right now, again, for the sanity's sake, it's probably easier if this is going to be inside of each of the functions. So whether it is a function return, or whether it is call or plus or whatever, each function will kind of create a temporary value on a stack and use that for the result. This is extremely inefficient, and long term, instead we should make use of temporary registers, because besides array X, there are other 15 registers that we could be using. But register allocation is an interesting topic by itself, and the way it is done usually in compilers is by using special representation and then doing optimizations, and I'm not exactly certain this is how I want to do it. So whatever we do with register allocation will be kind of a researchy thing, and I don't want to dive into that right now. So inefficient it is. Great. We have somewhere this nice thing of declare variable. I believe yes. So we're gonna make use of that. And declare variable returns to us an operand, which is stack. Probably it shouldn't be called declare variable. This should be called reserve stack. Stack. Reserve stack. Or reserve stack space. I don't know which one is better. Reserve stack it is. Operand temp is reserve stack. What do we need to reserve? Right now we will probably hard code the size of the reservation to always be 8 bytes, but the more I write this kind of stuff, the more hard coding there is, the more I'm certain that one of the next things that needs to be done is to go through the whole compiler that we have right now and make sure that we propagate the sizes of the variables correctly and are very careful with this. I probably will do it in the video, or maybe most of it will be done in the video and some cleanup of the video, but we'll see. So we need to pass, let's rename it to builder to match how it's called in other places. Reserve stack, builder 8. Again, to do, correctly size the temporary value. Okay. So we have our temporary operand on the stack, and now we need to return a value which we promised to the caller. Okay, that value will have a descriptor, and we just take the descriptor from the a value. So we say a descriptor. Like, it would be strange if basically we say that the first operand is what determines the return type, and we don't hardcode integer because technically we can also have pointers, and especially pointer plus immediate is kind of a common operation that you do, at least in the CLand. Maybe once we have more high-level definitions for this language, it's not going to be the case, but for now, let's keep it as is. And operand is our temp, right? So this is like this. So we created this temporary operand, but we didn't actually move our value to the right place, which is going to be move from REX to temp. So remember, in assembly, usually the first argument is the target and the second argument is the source. Or should I say in x86 assembly. Okay, let's have a quick look. We move the first value into REX. We add second argument to REX. Then we move the result onto the stack and we return that result. Obviously, if I try to compile now, a lot of things will break, but that's fine. We will slowly fix them up. So here's what is broken. This was our reserve stack. That's good. What does assign do? I need to remember. Assign is actually move. I'm not sure this is a form that we will want to have long term, but I guess it's fine for now. Okay, so we don't have mutating plus anymore. Instead, we have just plus. And since plus also accepts a value, we probably should make plus accepts actually a reference or a pointer. Oops, wrong button. I meant to press this one. To bookmark this, value star. A bunch of switches to arrows. B operand. Where else do I need to do? I guess here. Okay. So X and x, right? But now this stuff actually returns a value. So value temp is this. Now we say that value temp2 is another plus. So we have builder, and then we add to temp y, right? And we return temp2. So let's check how this works. Oops. Not quite. Function from operand. Yeah. Honestly, I think our reserve stack should also return a value and not an operand. Let's make that change, shall we? Value, value, value. If it doesn't return a value though, that means that we need to provide a descriptor for it and not just byte sized, or maybe later on it would be just the descriptor. So let's do that way. That's probably better. Okay. Turn const value descriptor is descriptor, and operand is, let's rename it to operand, like so. It's fine. We now don't have the byte size, so instead we say byte size is another to do. Again, about sizing. Say we should take the size from descriptor when it will be available there. Okay. It's good. Now I can say value temp, and we can remove this comment because it's no longer true. Here we say temp operand, and we need to provide a descriptor, as we said, and that descriptor will be a descriptor. Good. Now we have value x and value y. We need to do this, and we need to do this. Whoops. Need to do something about my control N. Maybe I should switch the shortcut to something else so I don't accidentally press it. Okay. Now reserve stack no longer expects a size. Instead, we need to provide a descriptor integer as an argument. That's good. I forgot to put the colon there and an ampersand, and we are done. So the nice thing about this is we are no longer kind of mutating one of the values, and this is way more like what you would write in something like C, right? If you just read this code and replace value with actual type, so you can say S64 temp is arg0 plus x. Obviously, we need to have this form that is not infixed for plus, because in C you can't do operator overloading, but this is fine. In general, this is more closer to the end state. And if we look into something like Compiler Explorer, let's actually open it in a new tab. And this is kind of what it will look like, right? We say int x is 1, int y is 2, and then we say int temp is and here's like value. So value plus x, temp2 is temp plus y, return temp. So if we have something like this, then the resulting code that we will do will also be roughly something like this. We can even later compare in Visual Studio Debugger what we receive. Anyhow, this builds. Let's try to run it and see if we messed up something. Indeed we did. So let's try to understand what's going on. Maybe I should open the instruction, and most likely the move or add instruction does not have the encoding that we want, but let's run it here. And let's go to this stuff and see where it blows up. F5. Okay. Ding. X and Y are fine. They have their stack locations. I mean, we didn't really change that, so that's fine. This also should be perfectly fine. And now we can step into the plus and see what happens. This passes through, none of them are AX. We try to encode moving to AX from another register, which is RCX. Okay, that succeeds. Now we try to add operand B, which is on the stack, to our RAX register. Does that succeed? Yes, it does. We find the encoding. That's good. So now it's good. And now we try to move into memory from the register. This also does succeed. So the first plus is not the problem. Okay. What about the second one? Assertions is fine. So now the first operand is on the stack, and the second operand is also on the stack. So we try to move to RAX from the stack, and this is where it doesn't work. Okay, let me recheck. So Oh yeah, this is actually quite interesting. So we need now to have a different form here that is kind of a reverse of what we have. So we have one that can move into register memory from register, but we want one that moves into register from register or memory. And this is this form, right? So it's gonna be 8b. Okay, let's see if that helps. Let's try to run this, and the tests have passed. Great. So now we have plus, and we can also create minus, which is going to be exactly the same. But first, let's stage the current state. Okay, plus, minus. It's basically exactly the same, except we now do sub instead of add. And maybe I will later on unify these two functions. Who knows? But for now, this is not the important thing. Let's try to test this. And since this function was called make increment, maybe what we should do is actually make it increment by 1, but in a slightly weird way, where we first subtract 1 and then add 2. So instead of plus, we say minus here. So we'll do minus 1 and then we add 2. Obviously, we need to update the tests as well, but this is not a problem. Where is our test? Yeah, this is the one that was 45 actually. It's 43, and we can rename this back into Inc64. It builds. Let's see if it passes our tests. Okay, we have the same problem of not finding acceptable encoding, which is fine, because we only have this form of register memory and immediate A, which we needed for stack reservation. But we obviously need to add more forms to this. So we would definitely need one that is like this. I assume there won't be opcode extensions. Let's basically copy these two from add into this is the right ones. Wait. I'm a bit confused, so let's not copy. First, let's find the right option. So we want this version that has the first thing as register and another one as register memory. So yeah, this one, and it is 2b. Okay. Maybe for completeness, since we are here, we can also add the reverse one, which is 29, and it is a register memory and register version. Extension is register as well, so this is fine. Now let's try to run our tests, and our tests have passed. Great. So we not only now fixed the plus to not be mutating one, but more what you expect out of a high-level language. And also we have now minus. Great. Now I will try to also add divide and multiply, but this is a bit more tricky and you will see why in a second, so I'm not sure we will be able to finish that today. Okay, but for now, let's add this stuff. Cool. So let's add another thing into here that will do a function that should make a function that multiplies by 2. Okay, that function will get an argument, and we expect an integer argument, and what it will do is, as it says, it will multiply that argument by 2. So we say value to return is multiply. We will definitely need to pass a builder. We need to pass arg0, and now we need an immediate, so we say value 2 is value from S64 to, like so. And we return whatever is the return. Now function type is S64 to S64, which I believe we do have. And the result is let's call it twice. We multiply 42 by 2 and we expect to have 84, right? Good. Now we need to have our multiply function. Where is our minus? Let's do multiply. Again, we need to have this assertion, although like technically we could support AX register here and we just stash it somewhere else and then we bring it back, but I think it's nicer to just have this invariant in our application that this should not be a AX register. Just save some headache. Anyway, getting back to multiply. So multiplication is more complicated than operations that we looked at before. The first thing about multiplications is there are two different instructions to do multiplication. One of them is unsigned one and the other one is signed one. And I think right now I will do the signed version because it is a bit easier to deal with. Like, if I understand correctly, unsigned deals better with overflow, and obviously it deals with unsigned values, but for now, let's just ignore that. Okay. And there's also different versions of multiplication instructions. They differ in sort of which register is used as the target register, and I will use this version that is kind of which is more or less symmetrical to what add does, if I understand this correctly. So this is this 2-operand form, and the first operand is multiplied by the second operand and then stored in the destination operand, which is the first operand, which is what we want. And so there is also this 1-operand form that does not truncate, and instead, like, you can get the value into 2 registers. But again, for now, this is not what I will be using. And I'm honestly even not sure what would be used by the C compiler, but we can check, right? So we can say mul value and return value times 2. And to have it closer to what we are actually doing, since we mostly deal with 64-bit values right now, let's get std int and switch this to int 6040 everywhere. This is just, yeah, hopefully closer to what we are doing. Let's wait for it to compile. Hopefully. Yeah, apparently there is a problem connecting to the server. I'm not sure if it's on my side or on their side, so while we wait, let's continue with the implementation. And the drill is basically the same. We move operand into A, we call imul, and then we also need to do a different to do here to do deal with signed, unsigned, and to do support double the size of the result. Maybe. I don't know. So let's recheck. Okay, so this is not my internet. I guess godbolt.ms got a bit dead. Let's is it godbolt.com? No, it's godbolt.org. Yes. Yeah. Let's look at you. So it actually changes the multiplication by 2 with addition, which probably is better. So let's force it to actually. Oh, interesting. Even if you do times 3, it still does an addition. So times 4. Okay. Now it's a weird instruction. Okay. Obviously, we need to give it. So this is kind of interesting, right? It means that there is special logic for probably up to 4 multiplication, because those are quite common to be replaced with something else. And there is also one for powers of 2, right? So if I do 8, it probably will also be SAL. Yeah, exactly. So it just shifts bits, but we can force it to do what we want. Okay, so it does use this form that does not have so it sort of doesn't use the extended result, which is nice to know. So I guess this is not so terrible that we are doing it this way as well. Okay, we do IMO, and this is the same. Let's try to build. Let's see what is breaking, and obviously it has no freaking idea what IMO is. Guess we need to teach it, and I will remove this version of the instruction. Here it will be IMO. That's good. Now we need the actual encoding for this, and the encoding for this is 0FAFR. Okay. Oh, this is the, yeah, this will not work because this is the register memory version. So I guess we will need to add this one instead with immediate. Oh, and it will be a bit of a problem because the immediate version requires 3 operands instead of 2 operands, which we right now do not support. What shall we do? What shall we do? I guess, well, I guess we are supporting 3 operands right now. It's not the refactoring I was considering to do today, but I guess we're doing it. So, run encoding type register, then it's register or memory, and then it is immediate 32. This should be, by the way, not immediate 32. This should be immediate up to 32, because it can be 16 or 8 depending on the other side, I guess. So yeah, anyway, wait, what's the difference between these two? Oh, this is the immediate 8 version. Yeah, gotcha. Okay, so this is the instruction that we want. It's 69. 69, that's good. And now we need to do a bunch of copy paste. In particular, we need to extend all the stuff with extra none. And I do believe that there are no instructions that take more than 3 operands. And the reason for this is because there is a limitation on the size of the instruction, I believe. It's like probably 16 bytes or something. It's written in the Intel architecture manual, but I already forgot what it is. So that's why you can't have too many different things. Okay, this is instruction thing, and we change this instruction to be 3 operands instead of 2 operands, and operand encoding is also 3. This also means that we will have to do some other changes as well. Let me recheck. This is 0069. Yeah, okay. Means that all of these instructions will now need this. This is like such a shame that like you can't rely on this to be 0. I mean, maybe you can in debug, but then you'll be very surprised in runtime. And this is one of the, I guess, more annoying things that exists in C. I will probably miss one or two of them as well, just by accident. So let's be careful actually here. And let's move more slower. Okay. Instruction. It's fine. I guess, yeah, this is how we can search for this. Okay. Good. Uh-huh. Let's do more. That's so fine. Okay, and now we're going in circles. So let's see what we have in errors. Yeah, this 0 ended up in the wrong place. It's fine. The same with this 0, I believe. Yeah, now it's missing one of those. Okay. This one is the same. It's in the wrong place. Okay. Let's see what explodes. Lots of stuff. Great. Always great to see stuff exploding. What is the first one? Should create a function that will return 42. Well, let's debug that. Spec. We want to do this. And yeah, let's just look at the assembly. I guess that will be the easiest way to debug what's going on. That's interesting. So somehow now it doesn't do anything at all. That's funky. Okay, before we jump into more debugging, we need to change this. I guess we can do something like static array. No. Size of instruction. Instruction operand encoding types divided by size of let's do it this way. U32 operand count is this. divided by size of operand encoding, whatever that is. Size of, yeah. I guess this stuff. It's not member of instruction. Is it not? Oh, it's a member of instruction encoding. So it should be encoding. Okay, this is better, and we can remove this fix me. And this means we can also change it here to not be 2. And here as well. And even here. Good. Let's try again. Still a bunch of errors. Let's see what is going on. Probably remove this bookmark. Instead, let's go back into here and run this. And this time we actually will step into this stuff. Okay, let's go inside of here. That's actually not what I want to see. I want to go inside of function return. Okay, function descriptor returns is to return. Descriptor okay, and what is our to return? Descriptor integer immediate 32. I mean, that sounds fine. This does not though. For some reason it thinks that the result is array X, but it's not. Oh, let's go back here. Right. No, it should be RCX, where the value. Ah, no, it's not even identity. So this is kind of strange. So how does value from 64 look like? Value from a 64 is doing this, which is descriptor type integer and then integer. Actually value from S32, but it doesn't really matter. So I'm a bit confused by that. Again, let's do that again. And let's look carefully at our to return stuff. Oh, yeah, this is interesting. This is one of those things that are annoying about C and why low level stuff is not exactly what you want to do. Yeah. So here the issue is that we are comparing an operand with the value instead of um, doing it some other way. So in general, I think I will just get rid of this check. And if we end up with array x copying to array x, oh well, that's fine. Basically, that's not how we should be doing all that anyway, so let's not try to prematurely optimize stuff and make our life more miserable. Let's try again. Okay, that's much better. It explodes in the right place where it says should make function that multiplies by 2. And this is because I did not actually write out the correct encoding. If we look into Compiler Explorer, it actually tells us that the correct way to do this is array x 5, 2, 3, 4. And this is not the way we are doing this. Instead, we are doing, so we should be doing this. Array x, like so. Good. Oop. That's fine. Let's see if that works. Okay. That's kind of interesting. Let me check instruction stuff again. So it is register, and then immediate, right? This is the form that we are trying to do. So it should be fine, but I guess we haven't had a 3 operand stuff before, so who knows. Or am I trying to add 64-bit value to it? Yeah, I am. So we need this version. Great. So we have not only added multiply, we also added a way to encode 3 operand stuff. I think as a final act, let's try to do divide to have all the basic operations inside, and divide is also in the same boat as multiply. It exists in signed and unsigned version, and we also will do signed version, but divide is even more interesting because it always stores the result in array x, and more annoyingly so, it overrides the RDX register with the remainder, which means we have to save and restore it after the operation. Otherwise, it will be quite bad. So let's start with that, right? We start with RDX temp. We reserve space for it for the stack. Then we do a move from to this rdx temp from rdx, and at the end we obviously need to restore this stuff. So move from rdx like so. And as you might have noticed, we are also very inefficient with stack space, right? We never actually free that space. So because this value is only necessary for the execution of this function, and later on it can be reused by other functions with no problem, but this is not how we're doing this right now, which is again fine for the moment, but something to think about in the future. Okay, so we are saving rdx. Let's actually make a comment. Save rdx as it will be used for the remainder. Here we now do restore rdx. Great. We could also technically use, well, we can't really use push and pop. Yeah, we can't really use push and pop, so ignore me. I thought we could use instructions to like push something directly on stack and moving from stack instead of reference stack as a memory, but it has all kinds of issues with the offsets afterwards, so let's not go into that. Okay, so we move the first operand to rdx, and I believe it's fine that both, actually we have to do it. We are dividing rdx by rdx, so it has to be inside rdx. Like there isn't even an option to do something else. Okay, so we move it in rdx, we do idiv, and here it is actually like this. Even more annoyingly, we might need to check if the operand is actually an immediate. So we can't deal with immediates right now. So another thing that deal with immediate operand. So we'll have to create another temp value that we'll actually use as the operand here. And maybe we should do that. So let's say that value star how shall we do this? Let's do it later. It's fine. I'm okay with this to do. idiv be operand. That's good. Then we reserve the space for the temporary value, and we what don't you like here? rdx temp operand. That's fine. Here there should be actually 0, 0. And what else? Like this. Yeah, now it can't find a div instruction, which we can easily add. So this is idiv, 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 and it's sort of actually interesting how we want to deal with this, because right now I'll write it as it's written here, but I think long term I would want to encode this information into instruction as well. And so we would have an encoding that says operand type register AX as a first operand, maybe. I don't know. This is F7. It also needs to have an extension that is 7. Okay, that seems fine. It builds and tests will run, but we are not actually testing the multiplication. So let's test it. At least let's test the version that will not require us to have immediate operand. So instead we will cheat and we will kind of create a proxy function for multiplication. We have arg0 and arg1, and we say we just want to divide arg0 by arg1, right? Call this unimaginatively divide function. We say divide 42 2, and we expect back 21. And we will need to do this, which means we also might need to add an extra type, which now lives in here. And indeed we do. So we have 3 argument 64, but we do not have 2 argument version. Now that works, and let's see if it works. It does not. Something crashes spectacularly. Well, this is why we have a debugger, and we can see what crashes. Integer overflow. That's interesting. Let's stop. Let's go into here. So the only way I can see integer overflow happening, I think, is if we divide by 0, but I'm not certain about that. So let's check what does the disassembly of this look like. So yeah, as you can see, it moves our 2 arguments in the right places, and then we go here. So divide RAX by RDX. If I and wait, okay, RAX is correct value, RDX is correct value, but maybe I'm misreading this and I can't actually use RDX as this source. Okay, is there an overflow here? Overflow is indicated by divide error, yeah. If source is 0, I'm a bit confused. Let's ask our trusty compiler explorer what should be the right way to encode this. B, A, although it's possible that it will not do the right thing. Let's see. So it uses double the size of operand in register and store resulting in register. Copies the signed bit of the value in the X register in every bit position in the DX register. CQ, CQ, O. Oh, interesting. So yes, we cannot actually use RDX as the source here. So I guess we will do the easy version of this now then, and say value divisor is reserve stack, and same as here, move here like this. So that actually fixes our problem with the immediate, because if it's immediate, it doesn't matter, it will be moved to the right place, to like a temporary memory. And the second thing, I guess we need to run this CQO. Yeah, I guess this is what we need to do. Okay. Let's do that. Let's put this right here next to IDIF. CVD, CDQ, CQO. Not sure how I want to call the actual instruction. I think I will call it CQO, but maybe that's not a good idea to do it that way. We'll see. For now, I don't know. So I'll just choose something that makes sense to me. Okay. Code extension, no. Instead of just the code 99, and it kind of does not have any operands to speak of. I could also do this. Maybe that's fine. CWG is a bit unfortunate name though, because it might conflict with current working dir, but for now that's fine. Okay, it should be like this, and we need to do our extension. So we say like this, and this also needs to be the right to do. Choose the right extension based on the size. But for now, this should give us the result we want. Good. The tests, at least it builds. Let's try to run tests, and the tests pass, although we need to fix the name of the test. That divides two numbers. Good. I think this video has dragged long enough, but we made really nice progress. To recap, we now support 3 operand instructions, which is great. We stopped using the mutating version of plus or add operation. Instead, we now have one that actually returns a value to us. We also added subtraction, multiplication, and division. With that, we have all the basic operations available to us. And in reality, we also have modulo, because divide gives the result in arrayx and the remainder in rdx, which we could support, but let's skip it for now. Anyway, I think this is time wrap up. Thank you very much for watching, and see you next time.